Okay, everybody. So, welcome to the second day of this workshop. So, I'd like to introduce Cynthia Rudin. She is a professor of both computer science and statistics at Duke. She works on a wide range of topics. She's done beautiful work in learning theory on topics like ranking. She's worked on very large-scale practical problems like applying machine learning to the power grid in New York City. And she's been thinking a lot about interpretability issues in machine learning. In fact, she was working on that long before before it dawned on anybody else that this was an important problem. So I'm excited to hear what she has to share with us today.
Great, thank you. Okay, so I work in interpretable machine learning, and over the years, I've seen the field of machine learning lean more and more toward more complicated models, even in cases where they're completely unnecessary. And I didn't just want to give it a talk that says, stop using black box models, because that's not really constructive, it's just destructive. And I wanted to tell you not just don't use black box models, but I wanted to tell you why you don't need them. Okay, so I'm going to give you an example of recidivism prediction in the criminal justice system. Like, they actually use predictive models to determine people's risk of being arrested in order to figure out parole or bail or for social services. And in some cases, the models that they're using are so complicated that it's easy to compute the predictions incorrectly, like to actually make typographical errors and get incorrect predictions. And this is a New York Times article right here. It's about a case where a typo in the input score of this predictive model called Compass led to someone getting years of extra prison time. And the typo was in his criminal history features. And so he didn't even know about the typo until he compared his score sheet to someone else's score sheet. And by that point, the decision was made and he was denied parole. And so this model, Compass, the model that was used here, this is actually a very widely used model in the justice system. And you would think that models like Compass would be really accurate, given that they use potentially over 100 features. And so we got some data from Florida to actually tell us how accurate this black box model is. So what we did was we compared Compass, which has a fancy name and is used, again, widely across the justice system, and it's proprietary. We compared that to our latest machine learning method at the time for optimal decision trees. So I work on optimal decision trees. So the method that we're comparing to is called Corals, which is certifiably optimal rule lists. And what we found was that we took the data from Florida and we created a machine learning model. It's so tiny that I can put it into the bottom of this slide. So it's like a little itty bitty model. And we were looking at that thinking that could not possibly be as accurate as this black box that's used in the justice system that uses maybe over 100 features. But the fact is it was. And what I'm showing you is cross-validation experiments on this Florida data set, and the colors are just the different folds of cross-validation. And Corals produces essentially the same model across folds, just the one that I showed you on the previous slide. And so we were kind of surprised. But not only do these two methods perform the same, but we tried all different machine learning methods and they also performed the same. We just couldn't achieve any higher accuracy than we could with the little tiny model on the previous slide. And some of these are very complicated, like boosted decision trees or support vector machines with Gaussian kernels. And then, of course, some of them are producing like the model that I'm showing you in the bottom of the screen there. Okay, so cool. All right, so I just want to go back to this point that maybe we're using complicated models when we don't need them. And there's been several studies on recidivism prediction in particular, and there doesn't seem to be any benefit from complicated models for rearrest prediction in criminal justice in particular. And there's been a lot of like debate over the fairness of Compass, but the fact is that I don't see why we even need Compass at all. Like, why are we even using it? So not only is there no benefit from complicated models for rearrest prediction, but there also doesn't seem to be a benefit for lots of other problems. Like I've listed a whole bunch of problems that I've worked on over the years, and for none of them did I need, you know, a really complicated model to get the accuracy of the top machine learning methods. Okay, and of course it depends on your data representation, because like for computer vision problems, you need a neural network. Like that's the thing it's just miles better than everything else, no question. And it depends on the representation of the data, because like neural networks are good when you need to create a good data representation. But if your data naturally come with a good data representation, then they all tend to perform the same. Okay, so then why are we using these complicated models when we don't need them? And the reason is because we like them. It's much easier to make a profit from a complicated model. It's also much easier to construct a complicated model than a simpler model. This is, kind of ironic, because, it's kind of ironic that complicated models are easy to construct and simple models can be very, very hard to construct. Okay, so let's say that we're doing supervised learning where we want to minimize a loss to make our models accurate. But now if you also want it to be simple, you have to constrain it to force the complexity of the model to be small, however you want to measure complexity. And once you get to constrained optimization, and depending on the constraints, the problem becomes much harder. And so like if you're doing decision tree learning and you just need to get a low loss, you can use CART, which produces some big tree that gives you a low loss. But if you want to get the same loss or better with a smaller tree, then that's factorially more work, like a huge amount more computational work to get something that's sparse, that's also the same level of accuracy. And just as a preview of what's coming later, the algorithm that created the model on the right is actually something that we're working on. It's a new decision tree method that produces accurate and sparse binary split decision trees. Okay, so if the problem on the left is about finding an accurate and sparse an accurate decision tree, then the problem on the right is about finding an accurate and sparse decision tree. And so if the problem over here on the left is about finding an accurate linear model, well, you can just do that with logistic regression, right? You don't need any special tool for that. But then if you want it to be sparse, then you might need to do some extra work for that. And then, the question, I want to know is, if you take all of the computational power that you have and throw it at the problem, how does that compare to if you were using an accurate and sparse decision tree, like something really tiny, or an accurate and very sparse linear model? Okay, so that's this is the question I want to answer. I want to know when these two sides are give the same result. Like, when do you not lose any accuracy by adding these extra simplicity constraints? Okay, so and what I want to know is, because the problem on the right is hard, I want to know before I solve it whether these two things are equal to each other. So can I determine whether I'm going to lose accuracy by adding these extra constraints before I actually solve the constraint problem? Because I want to know if it's going to be worthwhile for me to solve the one on the right. Okay, so in other words, can I determine the existence of a simple yet accurate model without actually finding one? Okay, so in this talk, what I'm going to do is I'm going to define a condition under which a simple yet accurate model is likely to exist. And that condition is going to be that the Rashomon set is large, and I will tell you what that means in a minute. And then I'm going to present computationally efficient solutions to one of the hard problems, which is I'm just going to talk about our work in decision tree learning. Okay, so the true Rashomon set is the set of models with low true loss. Okay, so this is, we're just doing supervised learning, and this is, the Rashomon set is the set of models that have expected loss below a threshold. And the expectation is with respect to the distribution from which the data is drawn IID. Okay, so the Rashomon set is the set of models, the set of functions here that have low true loss. And I claim that if the true Rashomon set is large, so if there are a lot of models that have low true loss, then I claim that a simple yet accurate model is likely to exist. Okay, so it's kind of like a big ocean theory, right? The bigger the ocean, the higher the chances that you'll find a big fish, right? And the larger the Rashomon set is, the larger the chance that you could find like a simple function kind of in the middle of that Rashomon set in there somewhere. Like there's so many good models that hopefully at least one of them is simple. Okay, so I'm just going to change my notation just a little tiny bit where the expected loss is just going to be represented by just L here. Oh, by the way, I've drawn a nice, really simple, nice, smooth function there, but the truth is that I could have chosen a really weird looking loss surface also. That's totally okay. Like I could have drawn a super weird loss surface and the Rashomon set could be disjoint, and that's totally fine. Okay, so I'm going to present the simplest abstract setting under which the thing on the bottom here, I'm going to present this as a very simple abstract setting under which this happens. Okay, so I'm going to define two hypothesis spaces. They're both finite. So we just have a finite set of models. We have simple models, which is F1, and then all models, which is F2. And then the simpler models are in the set of all models. And then here, I'm going to take F1 uniformly drawn from F2 without replacement. And now I know it's abstract, and I know that simple models aren't randomly drawn from a more complex model class. But in reality, as long as each complex model can be reasonably close to a simple model, like can be reasonably approximated by a simple model, then the idea of this is going to same idea is going to work. Okay, so I want to define F2 star. It's the best possible model if you know everything. Like if you have the whole population and if you have all the functions, then F2 star is the best you can possibly do. It minimizes the expected loss over all the functions. Whereas F1 hat, that is the best model that you could produce because you're only allowed to use simple functions and you only have the training set. So I want to compare, I want to compare these two models together. How well can you do with what you have versus how well you could do if you knew everything. Okay, so I'm just simplifying notation there again. So L is expected loss, L hat is empirical risk. And so what I want to know is whether the best true risk of the complex class, so this guy, I want it to be close to the best empirical risk of the simpler class. Okay, so I want to know what is this difference here, and I want that to be small. Now, this is not regular learning theory, because in regular learning theory, you would have the same function here and here. But here I have two different functions. I have F2 star, which is the best model if you knew everything, versus F1 hat, the best model that you can produce with your data in your simpler function class. Okay. Now, that bound is going to depend on something called the Rashomon ratio. And the Rashomon ratio is the fraction of models that are good. It is the fraction of models that have a low loss. All right, so I just put all the notation up at the top so that we don't accidentally forget any of it. And the theorem goes like this. It says that for epsilon greater than 0, with high probability, and I haven't told you what that p is yet, with respect to the random draw of functions from F2 to form F1, and with respect to the random draw of IID data, these two quantities that I care about are bounded by a function of the size of F1, which is the smaller function class, and this p here, which I hadn't told you earlier, depends on the Rashomon ratio. Okay, so if the Rashomon ratio is large, that's a negative and then that's a negative, so this p is larger. So as the Rashomon ratio gets larger, the probability with which this holds is larger. Okay, so the empirical risk of the best thing I can do on my training set compared to the best thing if I knew everything depends on this Rashomon ratio. So you kind of get the best of both worlds. You get like the complexity of the simpler function class, and the bound is nice and tight. So I know it's a little inscrutable, so I'm going to give you some examples. So for instance, if your function class has 100,000 functions in it, and at least 1% of them are good, then the bound holds with 99% probability when you have at least 526 simple functions. All you need is 526 simple functions. And as long as you have 1% of the models that are good, the bound holds with 99% probability. And then even if I reduce my Rashomon ratio to 0.5%, so only 0.5% of the models are good, then the bound holds with 99% probability when I have at least 1,051 simple functions. Okay, so this gives you a sense of really what this bound is trying to tell you, which is that if the Rashomon ratio is sufficiently large, then with high probability, the best empirical risk over the simpler class F1 is close to the best possible true risk over the larger class F2. Okay, and the generalization guarantee comes from F1 and the size of this Rashomon set. Okay, so I know that, like I said, I used a really unrealistic setup here because I had F1 being randomly drawn from F2. But in the paper, what we did was we replaced this random draw assumption with smoothness assumptions, or the assumption that the Rashomon set contains a large ball of functions. And so when we do that replacement, we could get theorems that have more realistic assumptions, but still have the same idea that you can bound these two quantities with respect to something that depends on the Rashomon ratio and the simpler function class. Okay, so these results that I just showed you and the other theorems that have the more realistic assumptions that I didn't show you, they suggest that if F1 is a good approximating set for F2, meaning that you can find that for every F2 you can find a nearby F1, and if the Rashomon set is large, so if there's a lot of good functions, then we might as well work with a simpler class because we're not going to be gaining any, losing any accuracy by using the simpler class. So for instance, if the set of decision trees approximates neural networks, and for my problem the Rashomon set is large, then I can work with decision trees and I'm not going to be penalized for not using a really complicated model. Okay, so I just want to point out that we're not doing standard learning theory here. Large Rashomon ratios pertain to the existence of models with good generalization. This is not regular learning theory where you're just going straight for the generalization of one model. Here you're talking about two different functions and looking at how those work relative to each other. The Rashomon ratio bound that I showed you, it doesn't work the same way standard learning theory works. It's not the same as a standard learning theory complexity measure. So the Rashomon ratio is not the geometric margin that's used in support vector machines. The margin is measured with respect to one model. Rashomon ratio is measured with respect to many. It's not the same as the VC dimension. VC dimension is data independent. Rashomon ratio is a property of a data set. It's not the same thing as algorithmic stability. Algorithmic stability is the property of an algorithm in the way it searches through a class of functions, whereas the Rashomon ratio is a property of that class of functions and not the way we search through it. It's not the same thing as Rademacher complexity, which measures the ability to fit noisy targets. Here, the Rashomon ratio uses fixed labels, so it's not the same thing. Okay, and it's not the same thing as a flat minimum because, as I showed you earlier, the Rashomon set could consider many local minima. It's just the fraction of models that are good. It doesn't matter whether they're in one flat minimum, although if you have a large flat minimum, then you would have a large Rashomon set. Okay, so far, our theory says that large Rashomon sets allow us to use simpler functions without losing accuracy. But that's what theory says. So what happens in practice? So I'm going to do some experiments. Normally, you can't measure the Rashomon set because that would force you to look at all the functions in a class, and that's usually impractical. But of course, we're going to do it anyway. uh, so, like I said, don't try this at home. But we did it, and what we found was pretty interesting. And as we found out, you don't actually need to calculate the Rashomon ratio in order to gain practical insights from it. Okay, so I did an experiment where calculate the size of the empirical Rashomon set. So we needed some way to calculate the size of the Rashomon set. And we couldn't calculate it for a very large, like a class of functions that we couldn't put our handle on. So we used decision trees of depth 7. So why decision trees of depth 7? Because they fit without overfitting, and they can be sampled. And decision trees of depth 7, they're a good approximating set for a much larger function space because they're able to fit our data sets well. They fit just, they fit well, and they don't generally overfit. And we're using data sets from the machine learning repository. Okay, so I want to also consider the larger set of functions that I care about, and that set of functions has to be able to include models from support vector machines, from boosting, from random forests. This is a kind of a bigger function class. Okay, so there's my function class there. And then the Rashomon set, again, is the set of good models. Okay, and I'm going to approximate that set with decision trees of depth 7. And the reason I'm doing that is because then I can get an estimate of the Rashomon set, the size of the Rashomon set. Okay, so then what I'll do is calculate performance of many popular machine learning methods on the data set and determine whether they perform similarly and do they generalize. Okay, so and I want to, the goal of the experiment is to determine whether A and B are correlated with each other. Our hypothesis is that they will be correlated with each other, that when there's a large Rashomon set, then it's going to include the functions from all these different machine learning methods. And then when you actually calculate the size of the Rashomon set using the decision trees, hopefully, if my hypothesis is correct, then it'll be large. And I'm going to tell you the results of the experiment before I show you the actual data. And the answer is that when the Rashomon ratio is large, so when the fraction of good models is large, then all the methods do tend to perform similarly and they generalize. But the interesting thing that we weren't expecting is that the reverse isn't always true. So, but we think that has to do with the way that we're measuring the Rashomon set. It turns out that if you have a bunch of extra features that don't do anything, they impact the denominator of the Rashomon ratio, but not the numerator. So let me at least show you the results of the experiment, or at least I'll show you a sampling of them. So we used 64 data sets for this experiment. We used a lot of different types of data, and including simulated data, categorical data, regression data, and so on. And what we found was that for the cases where the Rashomon ratio was large, we found that all the methods, again, tend to perform the same. Like these are 4 different data sets and all different, like 5 different methods. They tend to perform the same and they generalize well. And when there's a small Rashomon ratio, we sometimes get results like this where the performance is all over the place. But again, sometimes we get still that everything generalizes well and everything performs well. And like I said, I think that has to do with our measurement of the Rashomon ratio becoming artificially inflated when there are some extra features that don't do anything. And we have some experiments in our paper that show why that happens and give some ideas about what to do about it. Okay, so we get a lot of information out of these experiments because they say that it's okay if you can't measure the Rashomon ratio in practice, because what we find is that if the Rashomon ratio is large, then all the methods tend to perform similarly and they generalize well. Whereas if the methods perform differently, we're likely in a situation where we have a small Rashomon ratio. And then another thing that we found something else besides the results I just showed you, something we weren't expecting. And what we plotted is something called the Rashomon Curve. And like I said, we weren't expecting to see this, but we found it on every single data set that we investigated. And I'll show you a cartoon of what it looks like. It's a plot of the Rashomon ratio, the log of the Rashomon ratio versus the empirical risk. And let's say that you take a hierarchy of function spaces like decision trees of depth 1, 2, 3, 4, 5 up to wherever. So these are function classes that are nested. And so the question is, what happens to this plot as we move down this hierarchy? Now, we're getting to more and more complicated function classes, so you can expect that the empirical risk would get lower. But what happens to the Rashomon ratio? Well, as you get more complicated function classes, you get more good models, but you also get a lot more in the denominator as well. So you get more in the numerator, but the denominator, the size of the set grows, much faster than the numerator. So what happens is that the Rashomon ratio decreases. And so what this plot ends up looking like is that when you start at the beginning, at decision trees of depth 1, 2, and 3, you tend to decrease empirical risk without changing the Rashomon ratio. And then something happens and it nosedives. It just goes boom. And you might get a little bit of overfitting in there, so it might go a little bit to the left, but it nosedives so quickly that you don't even see it. And there's always some kind of turning point. There's always some kind of like elbow, and you might not even see the whole curve. Like you might even just see part of it. And like I said, we've seen this with every single data set we've experimented with, and not just for decision trees, and all different kinds of problems. And it always,
Cynthia,
yeah.
there's a question from the audience,
Oh, okay.
and the question is, what is the x-axis? What is the empirical risk of the function class?
Oh, if we're doing classification, it's classification error, and if you're doing regression, it's squared error.
So it's the risk of the best function in the class?
It's the risk of the best function in the class.
Great. Thank you.
Yeah. Okay. So anyway, yeah. So like I said, we tend to see this for all different data sets. And like I said, usually, or you might not see the whole curve, but you generally see at least some part of it. Okay, so I'm just showing you some samples there. Now, to go from training set to test set, that's where standard learning theory kicks in. And that's much easier because learning theory tells you that for simpler function classes, you should be generalizing better. And then as you get to more complicated function classes, you tend to overfit more. And so what you'd expect is that the best performance is somewhere around the elbow, because that's where you're getting sort of a good mix of low empirical risk and good generalization. Okay, so this is what we call the Rashomon elbow, and I just want to show you these experiments. I decided to put all 64 of them on one slide, just so that you could kind of see that across all of these data sets, we're getting these very, very consistent results in that you're always seeing these Rashomon curves. And it's either across and down, or it's straight down. And I'm going to zoom in to show you a little bit more about the generalization on these curves, so you can kind of see what's going on. So, so sometimes the learning theory, this is learning theory I'm talking about, sometimes the theory really tells us what's going on, and you actually do see kind of exactly what you'd expect from learning theory, that the best performance is right at the elbow and that it's better than the others. You tend to overfit when you go further down, but sometimes we always generalize, like if we have enough data, or it just always generalizes. And then sometimes we never generalize, and that's just thanks to learning theory. But in all of these cases, the Rashomon elbow is not a bad choice, right? It's not a bad choice for any of the cases when any of these things happen. So it might be a good choice for model selection. Okay, so the elbow is a good place to be, but in real problems, we don't usually end up having the whole curve, right? You just end up on part of it, and you don't always know which part. And you might want to try to figure out where you are on the Rashomon curve in order to determine whether we're below the elbow. And remember, we usually can't measure any point on the curve. So in this part, if you're in this part of the curve, the best model for each of the different complexity levels has different performance. So for machine learning, you would have different machine learning methods producing models of different levels of complexity. And so if each of the different machine learning methods performs differently, then you're probably on this part of the curve. And then if, on the other hand, no matter what complexity level you're working with, if you choose, like if the empirical risk is the same, like within reason, obviously, so you don't overfit tremendously, then in that case, if you have all the machine learning methods performing similarly, even if they're of different complexity classes, then the models that you're working with might be overly complex, and you could potentially reduce complexity to find models that are simpler or generalize better.
So there's another question.
Okay.
And so the question is, would you expect to see something similar no matter what you put on the y-axis, as long as it represents something that relates to the complexity of the function class?
So the answer to that question is that how do I say this? I'd like to hypothesize that would be true, but I think that this is new enough that I don't want to say it definitively, but I'd like to hopefully say yes. I think that's probably the answer to that. I mean, we've been measuring the Rashomon ratio in different ways, and we seem to continue to find this, but it's possible that some other explanation is true. We're just posing a hypothesis. Okay, but I think it's solid enough that it at least tries to explain what some of the things that I and other people have been observing across problems and across data sets, right? There are some problems like ImageNet where the field has been like designing more and more complicated models and it reduces error. So maybe we're still on like this part of the Rashomon curve. And then in that case, adding more complexity might help. And then on the other hand, if you think about problems like MNIST, where it doesn't matter which method you use, you get 100% accuracy. And in that case, maybe we should be aiming for simpler models that might generalize beyond MNIST and might be simpler and more interpretable. And then there's a ton of problems like the kind I usually work on. I usually work on like high stakes decisions, and so I always end up in this regime where I just can't get low empirical risk no matter what I do, and if I try, I'll just overfit. And in the problems I work on, the Rashomon ratios tend to be pretty large, and so I can get simpler models without sacrificing accuracy. Okay, like for the Florida rearrest problem, then here's where we can get some very simple models without sacrificing accuracy. Okay, so an easy check then for the possible presence of a simpler yet accurate model is that if you pick several of your favorite machine learning methods and you run them all in the data and they all produce different results, then the model class might be too small to include the elbow solution. Or it could be that your data benefits from a specialized hypothesis space. That could be true too. And so in that case, you might want to broaden the horizon and use a more complex model class. Whereas if you if all the methods are performing similarly, then your model class might be larger than necessary, in which case you might want to delve in and find specialized models with specific properties like interpretability. Or and that would allow you to look up to improve generalization without reducing accuracy by moving yourself toward the elbow by decreasing complexity. And like I said, it's just a theory. but I think that it's a reasonable explanation of what could be going on in problems like rearrest. Okay, so back to the talk outline, and I've defined my condition, which is that the Rashomon set is large. And like I said, you don't need to calculate the Rashomon ratio. You can just try lots of different machine learning methods, and that'll just give you a sense of whether simpler solutions might exist for your problem if all the machine learning methods are performing similarly. Now, a lot of people don't believe me about this, or they're not interested, and that's fine. But sometimes it can get kind of silly. So before I talk about decision trees, I want to tell you a story that happened earlier this year. Now, I entered this explainable machine learning challenge in 2018. Now, we found out about the challenge and we decided to enter it. It's the first ever explainable machine learning challenge. And the data was given by FICO, and it was loan decision data, which obviously during the current pandemic era is going to be kind of important. But in any case, the goal of the competition was to create a black box for the FICO data and then explain what the black box was doing afterward. And we got the data set. It was a nice big data set. And we looked at it and I thought, could I be wrong? Could this be like a data set with a good data representation that doesn't permit an interpretable model? Like, let's take a look at this. And so I said to my students, okay, let's try running a whole bunch of different machine learning methods on it and see if they all perform the same. And then that'll tell us whether we could try to find an interpretable model for this data set. And so they went away and then they came back a couple of days later and they said, yeah, all the machine learning methods are performing the same. And so we pretty much knew at that point that we could construct an interpretable model. And so at that point we had a conversation because, okay, the competition says create a black box and explain it. But we pretty much know at this point that we can create an interpretable model for this data set. We don't need to create a black box and explain it. And so we were thinking about it, what would the judges think and so on. And we just said, oh, forget the judges. For a problem as important as loan decisions, we need to try to create an interpretable model if we can, at the risk of losing the competition. And so we created this beautiful model with a beautiful visualization tool that you can play around with. It's all interactive. It's online. You can play with it. And you enter the features and it has everything comes up in colors and so on. And it combines all the scores together. It's nice. It's like stacked logistic regression models. And so it's like sparse stacked logistic regression models. And you can see like you get points for your percent trades that are never delinquent, and you get points based on your month since most recent delinquency, and all the points add up and so on. So we did this, and we were right that the judges, we sent it in, and the judges had no idea how to judge it. They actually didn't use the visualization interfaces at all, and we bombed in the competition. We did really badly. And but luckily for us, the judges realized that their judging criteria wasn't great, and so they saw value in what they did. So they created a prize for us. It was so nice. So they wrote that we went above and beyond expectations with a fully transparent global model and a user-friendly dashboard. And someday we'll get that $3,000. No, I'm just kidding about that. But in any case, I was delighted that the judges saw value in creating interpretable models rather than just explaining black boxes. And so we decided to submit it to a competition, sorry, not a competition, a special issue for a journal. And in order to do that, we had to know whether it was within the scope. And so I sent an email to the editor of the special issue and I said, dear esteemed professor at Fancy Esteemed University, we have this paper that we'd like to submit to the special issue. We don't know whether our paper fits into the scope of the special issue. It's not a traditional methodology paper. Its contribution is an analysis of the FICO data, including a machine learning model that's interpretable, and it actually won this thing. And what do you think? Will you allow us to submit it? And the response was, dear Cynthia, thanks for reaching out. This is an interesting paper, but I'm afraid it's not a good fit for the special issue. It's also related to my own recent work on explainability of neural nets. Is the FICO data still available? Could you share it? So basically, I send the guy saying a paper, like, you don't need a black box for this data set. And he sends me back an email saying, I don't care about your work, but can you send me the data so I can create a black box for it and explain it? And that's unfortunately the state of where things are at the moment. And I don't know if there's anything I can really do about it, but at the very least, I could, present some computationally efficient solutions to create interpretable models, and hopefully people might consider using them someday. So I decided that I would talk about our work on decision trees. My lab works on 4 topics, really. Decision trees, sparse linear models with integer coefficients. Some of these models are actually used in intensive care units in hospitals because they're so interpretable that doctors can use them for even high stakes decisions. We work on matching for causal inference and interpretable deep neural networks. So what I'm going to talk about now is decision trees. And we found some applications for this in material science where neural networks actually don't perform as well because the data representation is not correct. Okay, so I'm going to talk about, like I said, our work on decision trees. Decision trees, they've been popular since the very beginning of machine learning. The main problem that's always plagued decision tree algorithms is their lack of optimality, because they've historically been these myopic greedy algorithms like CART and C4.5, where they construct the trees from the top down. And the problem, these algorithms, they construct the tree from the top down and then they prune it back greedily afterward. And the problem is that once you choose the wrong split at the top, there's no way to undo it. And so sometimes the algorithms spend the rest of their splits trying to undo a bad split at the top. So the problem, though, is that it's hard to improve over the greedy methods because decision tree optimization is hard, both theoretically and practically. Like there's a combinatorial explosion in what the splits are, and the number of trees we could consider is really large. So we'd been trying to use mathematical programming solvers to do this for a long time, but the fact is that those solvers are just not optimized for this problem, and so they don't work that well. And some people have tried neural networks, but neural networks are really not the right tool to solve these hard discrete optimization problems. So in our work, we're aiming to provide the first practical algorithms for producing optimal sparse binary split decision trees. And we're using regularized misclassification error here, where the first term is just the fraction of points that are misclassified, and then sparsity is just the number of leaves in the tree. And we're not using greedy splitting and pruning. Instead, we're developing a specialized branch and bound method to solve the problem to optimality, leveraging computational caching. So we solve it to optimality. There's no greedy splitting and pruning, and then we're using branch and bound combined with very careful data structures and computational caching. So this is an example of the result of what happens when you solve an optimization problem like this. You get a tree that looks like this. It's a binary split decision tree, and this one happens to be on that same Florida rearrest data. Okay, so the approach uses several important insights. And first, we have a collection of theorems. They're analytical bounds, and they show that some partial trees can never be extended to form optimal full trees that minimize that loss on the previous slide. Okay, and so the bounds, they can do things like so if we try to construct a tree like this, right, where if we try to split on rush hour, and then we're thinking about splitting on tornado here, but the fact is that there hasn't been a tornado often enough for us to warrant a split there for a sparse decision tree. And so we actually have a theorem that says, okay, if you don't have enough data that goes into that branch, then I can prove that no child of this will ever be optimal. And so I can exclude it and all of its children. And also, if we can prove the tree can never be accurate enough with a given split, then we know that split and all of its children are not possible when creating an optimal solution. We also have theorems that relate the number of leaves to the accuracy of the tree. So if you are not accurate enough for how sparse you are, then that tree and all of its children will be excluded. So it's a way of sort of chopping off large portions of the search space. Okay, and then we also represent a tree by its leaves rather than representing it the way I have on the screen. We just represent the tree by its collection of leaves. So here, rain, construction, and traffic, that's the leaf. And then that's this leaf, and so on. And so while we're working in this algorithm, we actually don't ever represent the tree this way. We always represent it just by this collection of leaves. And this allows us to it's a very convenient way to work with trees. We store the bounds and intermediate results within each leaf so that we can continue to calculate as we go down. So when the leaf splits, it's just another the leaf would split into two leaves. Okay, we also have a data structure called a permutation map. And the permutation map discovers if we've already seen a tree before. So for instance, if we end up constructing the same set of leaves, but from a different tree, which is definitely possible. Like if we somehow end up with exactly the same collection of leaves from if the tree was flipped somehow differently, then we don't want to continue to grow that tree because we've already seen it before. We've already processed it and dealt with it. And so whenever we see a new tree, or whenever we come across a tree, we go and look it up in the permutation map and say, have we already dealt with this tree before? Because if we have, we're not going to do it again. Okay, yeah, so if we see this collection of leaves again, we know that we've handled it before and we're done. And then we represent each leaf as a bit vector that describes the data that falls into it. So for instance, for the first data point, if it was rain, construction, and traffic, if the data point fell into rain and construction, then there would be a 1 there. Okay, so it's a bit vector that describes where all the data, which data are captured by which leaves. And that allows us to use very fast bit vector operations to compute all of our bounds. And so we can traverse the search space very quickly and chop off large pieces of it very quickly. Okay, and then we also use incremental computation of the objectives and bounds. So in other words, when we're going to compute the objective for a new tree, we don't compute it from scratch. We use the information we've already computed. So for instance, here, Friday, if we already have a bound for this node here, this is our lower bound that we've gotten from our theorems, and then this is the vector of points that are captured by it. Then we can grab that information and use it when we're computing things below it. So here the bound would be used when we compute the next bound for the next node, and then what's captured down here has to be a subset of what's captured up here. And so we're taking that information and using it as we evaluate our bounds and construct our trees. Okay, so this combination of the bounds, the leaf-based representation, the permutation map, caching of intermediate results, and all this incremental computation leads to a very fast implementation, and it's able to be used. The code is publicly available, and yeah, you can give it a shot. Obviously, it's solving very, very hard problems, so you're not going to use it for massive data sets, but it's good for if you have like a data set of the size that that I usually run into in criminal justice or in healthcare. So in summary, I've just defined a condition under which a simple yet accurate model is likely to exist, which is that the Rashomon set is large. And I showed a simple check for large Rashomon sets, which is to try a whole bunch of different machine learning methods. And if they perform very similarly, then it could mean that the Rashomon set is large. And then in that case, you would try to find simpler models that have the same level of accuracy. I also introduced these Rashomon curves, which is this characteristic curve that seems to somehow exist for all of the data sets that we've worked with, which is the Rashomon, the size of the Rashomon set versus the lowest empirical risk in the class. And then I showed computationally efficient solutions to some of these hard optimization problems. So for instance, the optimal sparse decision trees problem. Okay, so that's all I have, and let me see if I can get out of here and try to figure out if we have any questions. Okay.
Yes, so there are you able to see some of the questions?
Yeah, I can see them now. Let's go back up
Okay,
here.
so the last two questions by Gil Tamari and Reza Samavi.
Okay. How does dataset size and diversity affect the ratio? Um, so datasets, I'm not sure. So dataset diversity? I don't understand the question. We haven't done affect the ratio. It's more a matter, I don't know. I don't know if I would say that those are the primary axes we would look at. Like we would normally look at things like the kind of complexity of the function class relative to the data set. So all of these things are mixed up in a way that I don't truly understand yet. So I'm not sure I can yet answer that question, but I think it's worth considering it. Yeah, so I don't know how to answer that one. Okay, so are you checking an exact match for the graph to avoid recomputation, or isomorphism is also being rechecked? Yeah, it's isomorphism. So so if you have seen the same set of leaves in a different permutation, any other permutation, then we know we've seen an isomorphism of that tree before, and so we don't need to go and explore that again. Slide 78. Slide 78. Where's slide 78? Oh, you just want the links. Okay, yeah, they're just on my website. You can, oops, yeah, yeah. I have a code page on my website, so you can always just find code there. Going back to the Rashomon curves, is your proposal equivalent to saying one should use the smallest function class that contains a function with zero training error? No. So we very often can't get to zero training error. My proposal is that we should use the smallest function class that contains a function that is at the same level of accuracy as the best machine learning method that you can get that doesn't overfit. That's my slide. Okay, that's my proposal. All right, so slide 77. Okay. Let me go back to look at some of the other questions here.
I think the other
Yeah.
ones were answered. So I have a couple.
Mhm.
So the first one is, so for the Rashomon ratio, is there sort of a Bayesian version of the story? It seems like it might fit very well in a Bayesian framework, where you have a prior distribution over models, and then you can talk about the prior mass of models with good accuracy and so on.
Um, we mentioned something very briefly in the paper about having a prior over functions, but we didn't. That's not something that we worked out. But like I said, we don't have all the answers to this. The paper's mostly posing questions rather than answering them. But we think that the questions are interesting and important. So I agree with you. I think that's an important question.
So another question is, so in your experiment, you were measuring the Rashomon ratio with respect to decision trees of a certain depth,
Right.
like I think depth 7. And then from that, and then after that, you were doing experiments with lots of different types of classifiers, linear classifiers and so on.
Mm-hmm.
So do you think it was important to measure the Rashomon ratio for a class like that, a non-parametric class like decision trees?
Yeah, I do think that was important because this decision trees, we needed to come up with a class that would be able to be a good approximating set for the class of functions that we really cared about, which was some weird combination of support vector machines and random forests and boosted decision trees. And so decision trees of depth 7 seemed to us like, for the problems we were working on, it seemed like it was a good approximating set. So that's why we needed something non-parametric and something flexible. That's why we chose that. If people are still thinking about questions, and I still have a couple more minutes, I thought that I would do something kind of weird because this is a weird time. So I thought maybe I would try singing a song, if you don't mind. Let me see if I can figure out how to share a different window, because I need you to see the lyrics. Where is it? Oh. Well, that is not working the way I was hoping it would work, but I think I could just share my whole screen. Yeah, it says application window. Oh, there it is. Okay, got it. All right, so I'm gonna sing you a song that I wrote for my class. And I've only sung this once before in public, and that was to my class. This is even more embarrassing. Okay, so it's a song about overfitting. As the evening rolls by, the sun has passed set. My code has a bug, and I ain't found it yet. I tried all kinds of trials, ablated large scripts, depleted my memory, search Stack Exchange for tips. In training it predicts easy, like a cheating gambler. But in test, it's a random guess. On the midnight oil, the fire's lit. Despite these flames, it's still overfit. I know all the secrets, you know that I do. I randomized, regularized, reduced dimension to 2. Reset the seed and reshuffle them all. Increase parameters and prepare again to fall. In training it predicts easy, like the sun in the desert. But in test, it's that random guess. The machine and I, we play this dreadful game, and overfitting has become my name.
Okay.
It's supposed to be about a guy who, like, like the guy in the bluegrass songs where he's like, out on his porch looking over a lake at sunset and he's all depressed. It's horrible stuff. This guy's a computer programmer and he's trying to get his code not to overfit. Yeah.
That was lovely. Thank you very much.
Thank you.
Okay.
Okay. Bye.
Bye, everybody.